Hello and welcome back. In today's video, I'm going to be going over the 2025 AP Statistics FRQs. If you have any questions, let me know in the comment section down below. Otherwise, let's get started. And for these questions, I'm going to be writing down the key points that you should be expecting to see in your answer. But if it's a numerical calculation, I'm going to be showing all the steps. So let's start off with 1A. You have a manager who has two box plots of gas mileages, country A and country B. So our manager wants to compare the distributions of gas mileages. So this is what you should be comparing. The range of data sets, the IQRs or interquartile range. You could compare the max or min values, and you can compare the median. These are some values that you can use in your comparison for the box plots of country A and country B. Now, part B. For the distribution of gas mileage for cars in country A, would the mean be greater than 18, less than 18, or equal to 18? And if we look over here, 18 is actually the median for country A's data set. So how do we know which one we expect to be greater? Well, let's look at the bottom and upper 50% of these data sets. The bottom 50%, for this bottom 50%, the data is actually very close to the mean. Data is much closer to the mean. But for the upper 50%, data is much further away from the mean. And we could also include the existence of our outlier, because that would greatly increase the value of our mean. And if you also wanted to give another example, you could note how the 75th percentile, the distance from that to the median, is actually greater from the median to the minimum value. Now you can use all of this to justify why the mean would be greater than 18 miles per gallon. Because that is going to be my answer for 1B. We expect the mean to be greater than 18 miles per gallon for country A, and you can use this in your justification. And now finally part C. We have two parts to this, CI. What is the range of our combined data set? So we're going to be merging country A and country B's data sets. Well, the range is going to be the max value minus the min value. The max here is 40. The min value is 14. So all we have to do is this. 40 minus 14 equals 26. That's the range. And now CII. What is a possible value of our median? Justify your answer by referencing the box plots shown. So when it says possible value, there might be more than one accepted, but my answer for this is going to be 24, and this is why. The upper 50% for country A roughly overlaps with the bottom 50% of country B. So if we were to merge these data sets, this combined section over here would represent the 25th and 75th percentiles. And if we look at the center of that, we're going to get our median for the entire data set. And the medians over here would be located here at 24, since they intersect here at 24 miles per gallon. So we expect the median to be at 24 miles per gallon. And this is because the upper 50% of country A roughly aligns with the bottom 50% of country B. And there's your answer. Obviously you'd want to explain this more, but this is the key idea for why I believe the median is 24 miles per gallon. Now that we've completed question 1, let's move on to question 2. And this is about a farmer and his precious cabbage field. However, these cabbages are being damaged by aphids, and he wants to evaluate the extent of this damage. So he's going to be doing 3 sampling methods. So let's see. Number 1, well, part A. Explain whether sampling method 1 is an appropriate sampling method to use to estimate the proportion of cabbage plants damaged by aphids. What's sampling 1? He's going to be selecting region 3 closest to his house and farthest from the river, and he's examining every cabbage plant in this region for damage. Well, now that just sounds like convenience sampling to me. The farmer is selecting the region himself to sample from without any randomization. So part 2A, yes, it is inappropriate, and this is because he's using convenience sampling, no randomization. And if you wanted to give a reason for why we need this randomization, then you could give any plausible explanation. Let's say that near the farmer's house there's actually some type of pesticide that actually scares off the aphids. Well, if we're not using randomization and selecting a few samples, then we're not going to be getting anything that properly represents our population. We're just selecting this one that's conveniently right in front of our house. So if you wanted to give a reason, you could say something like, perhaps there were pesticides near the farmer's house in his storage, which reduced the proportion of aphids at region 3. That could be maybe why he selected it. We don't know, but this is a reason as to why you wouldn't want to use convenience sampling and why randomization with a few more samples would be much better. Well, that's an example for 2A. Next, 2B. Using sampling method 2, the farmer randomly selected row E and examined every cabbage plant. That's right over here, right next to the river. If the farmer's belief is correct, determine whether the selection of row E is likely to provide an over or underestimate of the proportion of cabbage plants in the field that are damaged by aphids. Justify your answer. Let's see. Row E is right next to the river. It's the closest one. But what does our farmer believe? Our farmer believes that things that are right next to the river are actually going to have greater damage. So let's write down some key points here. Using row E, we expect it to be representative of our population. In reality, if we assume the farmer's belief to be true, then row E would have a much greater proportion of aphid damage. Therefore, let's see what we're asking for. We're trying to see if it's an overestimate or underestimate for the entire field. This is going to be an overestimate. So we're going to say overestimate, because if the farmer's belief is true, then cabbages in row E are going to have a much lower proportion of cabbage damage. And that's the answer you would want to give for 2B, or something containing some of these key points. You just want to mention the fact that row E, we expect it to be representative of our population, but in reality it's not, so it's going to be an overestimate if we assume the farmer's belief to be true. Well, on to part 2C. Using the information in the diagram, so what we have over here, describe how to estimate sampling method 3. Now this sounds like stratified random sampling to me. So what we're going to be doing here is making 5 hats. Make 5 hats named A through E. Then, for each hat, put 5 slips of paper in corresponding to the regions and to the numbers of the regions stored in that row. So for example, if my C hat is going to have 11, 12, 13, 14, 15. For each hat, randomly select 1 slip of paper. This slip of paper is the region that the farmer will be sampling from. And that's one possible answer for what you could say. You make 5 hats or 5 containers, anything. You put the corresponding numbers for that row in the hat and you randomly select 1. And you move on to the next hat. That's an answer for 2C. We just completed question 2, let's move on to question 3. Mrs. Faye is a manager at a restaurant and wants to improve the dining experience for her customers, and she's using a digital music service. She takes 1 song at random to be played. What's the probability that this song is a rock song? Well, we have 1,000 total songs, and there are 100 rock songs in total. So for part A, we're going to be saying that it's 100 divided by 1,000. That's equal to 0.1. For part A, suppose 2 songs are selected at random. What's the probability that both are rock songs? Now, you might think that we're doing 100 by 1,000 times 99 divided by 999. But we're being told that any song can be replayed at any time. I'm going to be assuming that this means selection with replacement. So all we're going to be doing is 0.1 times 0.1 is equal to 0.01. So that's part A. That was pretty easy. Now, on to part B. In a 1-hour period, we have 20 songs that are played, and any song can be replayed, and Miss Faye wants to find out how many rock songs will be played in a typical 1-hour period. So let's say 3B. We have 3BI and 3BI, so 3BI. Define the random variable of interest and state how the random variable is distributed. So Miss Faye wants to find out how many rock songs are played. So X is the amount of rock songs played in a typical 1 hour period, or 20 songs. And now we have to find the expected value of that for 3BII. Well, if we look over here, actually, let me define it first. I forgot to say that. X is going to be a binomial distribution, and this is why. We have a fixed amount of trials, 20 songs. And since we have a fixed amount of trials and we have a fixed probability, we're going to be using a binomial distribution. So X is a binomial distribution. So 3BII, find the expected value. Well, the expected value is actually equal to your mean. And what's our mean? It's n times p. N is 20, p is 0.1. So we expect 2 rock songs to be played every single hour. Now, recall that in every 1 hour period, 20 songs will be played at random, and any song can be replayed at any time. Then we have to determine the probability that 4 or more rock songs in a single 1 hour period will be played. In order to answer this, we have to think about the binom CDF function. Let me just write down 3CI. Good. Now, the binom CDF function, let's say the trials is 20 and we want 3 as our X. That tells me the probability of 0 or 1 or 2 or 3 songs playing in the 20-hour period, in any order. But if I did 1 minus that function, I would get the probability of 4 or more rock songs playing. Because remember, if I'm not having 0, 1, 2, or 3 songs playing, I'm having 4 or more. Because we eliminated that possibility of 0. So in order to answer this, we're going to be doing 1 minus binom CDF. And if you don't know how to answer this, open your calculator, go to distributions, and go all the way down to, I'm on my calculator right now, to binom CDF. And you have your trials first, you have your probability, you have your X value being 3. Because remember, you're doing 1 minus, you're doing 3, and that's it. And when you do this, so let me just type it in, 20.1 and 3. And if we do 1 minus this, we get the probability to be around 13%, or 0.13295, or 1330. Now, suppose 4 rock songs are played during a particular 1 hour period. Does this provide strong evidence that this process is not random? Justify your answer without doing an inference procedure. Well, let's look back at our past question. We just found out that it's a 13% chance for 4 or more songs to be playing in a 1 hour period, rock songs. Since this 13% chance could have occurred by chance alone, since it is still a large probability, we cannot infer that there is any evidence to suggest that this process was not random. Let's fix the spelling mistake. But in essence, what I'm saying here is that this 13%, it's not less than 5%, which is our usual threshold, but it's still large enough. So we can't say that there's any strong evidence for this not being random. This 13% could have happened naturally by what we call chance variation. So no, we don't have any strong evidence to suggest that the song selection process was not truly random. Now, let's move on to question 4. So in question 4, we have a student who's in a country, in a high school, and there's a certain app being used all around this country. And researchers indicate that 22% of high school students use this app once a week. But Karen, a student at a high school, believes that this proportion is actually much greater at her high school, and she's going to be doing a test to find out. She does a simple random sample, and we have to do an inference procedure to find if there's convincing statistical evidence to support her belief. So let's get started. We have to choose an inference procedure first. Then what am I going to be choosing? I'm going to be choosing the one prop z test. This is the most appropriate test for our situation, as we have one proportion and we're doing the test for that. But let's define our hypotheses first. First, we have our null hypothesis. It's H subscript O. I'm just writing it as HO. HO, our null hypothesis, is going to be our null hypothesis is that P is equal to 0.22, and our alternate hypothesis is P is greater than 0.22. But what is P? Make sure you define this. P is the true proportion of students at Karen's high school that uses the app. So we did our choose step. Let's do the condition checking. Because remember, you actually have to check the conditions here. So what are the conditions? First, we have the normal condition. And for this, we assume the null hypothesis is true. So we're going to do 0.22 times the sample, that's 130, and that's 28.6. So 0.22 times 130 equals 28.6. Since this is greater than or equal to 10, we pass the normal counts condition. Now normally you have to do the 1 minus p as well. I'm not going to do it for now because if you pass the smaller proportion, you are 100% going to pass the larger proportion. So let's move on to independence. The independence rule is that your sample size should be less than 10% of your population. Our sample size is 130 and our population is more than 2,000. Since our sample size of 130 is less than 10% of 2,000, 10% of 2,000 is 200, we can assume independence in our calculations. And finally, we're going to be checking for a simple random sample. We need some randomness in our experiment. And there was a simple random sample done. The data was collected via a simple random sample. Well, we met all the conditions. Let's actually calculate this now. And now there are two ways you can calculate this. You could either use the z-test function on your calculator, the one-prop z-test, or you could use a test statistic and put it in the normal CDF function. For this video, I'm just going to use the z-test function in your calculator. But remember, either method gives you the exact same answer. But for my calculator, what I'm going to do is, if you're on a TI-84 plus CE, go on over to Stat, Tests, and click on 5. That's the one-prop z-test. Once you hit enter, you're going to enter your information. So P null is equal to 0.22, your sample size is equal to 130, the number selected in your sample is 38, and you're trying to see if this proportion is greater than your null hypothesis, and calculate. So what I would write here is, using the one prop z test function with x is equal to 38, n is equal to 130, p null is equal to 0.22, and for checking the probability that the proportion is greater than PO, we get a p-value of 0.20232. Now that we have our p-value, we can actually do our conclusion now. Since our p-value of 0.0232 is lower than our significance level of 0.05, we can reject the null hypothesis. We have strong, convincing evidence in support of Karen's belief that more than 22% of students at Karen's high school use the app. And that's the answer for question 4. Now, let's move on to question 5. Now we're here at question 5. According to a 2017 survey, the mean number of bedrooms in newly built homes was 2.9. But Rodney here believes that it's actually different in 2024, and he wants to investigate this. So let's start with question 5A. 5A. If a house from the sample is selected at random, what's the probability that the house has fewer than 3 bedrooms? Well, if it has fewer than 3, it has 1 or 2. So that's easy. We're doing 0.12 plus 0.22. 0.34. That was very easy. But let's do part II now. This was part I. Let's see what AII is. What is the mean number of bedrooms for the sample of newly built houses? Well, if we go over to our formula sheet here, we can see that for a discrete random variable x, now this is what represents that, our mean is multiplying every single number here by the probability and adding it up. So for this, I'm going to write it in my calculator, but this is what you would write down. You would write down 1 times 0.12 plus 2 times 0.22 plus 3 times 0.28 plus 4 times 0.22 plus 5 times 0.14 plus 6 times 0.02. And that gives me the value of 3.1. So E of x is equal to 3.1. That's the mean number of bedrooms or expected number of bedrooms for newly built houses in 2024 off of this distribution. Now, Rodney is going to be using a one-sample t-test for a population mean to test his belief. So that's going to be part B, 5B. So in the context of Rodney's investigation, we have to state the hypotheses for this test. Let's do that. H null, H alternative. Now remember, we are given that the mean number as per a national survey was 2.9, and Rodney is trying to dispute this. So remember, I'm not using u, I'm trying to use the value of mu. It just looks like a u now. So our null hypothesis is that mu is equal to 2.9, and our alternate hypothesis is that mu is not equal to 2.9. So he's trying to say it's different. Remember, we have to define the value of mu. Mu represents the true mean number of bedrooms built in new houses in 2024. New houses in 2024. And in context, explain what a type 1 error would be. A type 1 error would be concluding that the true mean of bedrooms in newly built houses is not 2.9 when in reality it is actually 2.9. That is what a type 1 error would be. Now on to part C. That's 5C. A different researcher, Keisha, suggests using a confidence interval, and Keisha made a confidence interval of 3.01 to 3.19. Based on this confidence interval, what conclusion can be made for Rodney's hypothesis test? Well, remember, Rodney's trying to see, and this is for 2024 by the way, Rodney is trying to see if this 2.9 value is even in here. But I don't see it. So what I'm going to say is, at a 97% confidence, we can observe that every value in the interval is greater than 2.9, and the interval does not contain the value of 2.9. Therefore, we are 97% confident that the true mean for the amount of bedrooms in newly built houses in 2024 is not 2.9. And there we go. That's a sample answer for this question. And now we're on to the much longer part of the AP Stat test, the inference question. Question 6. So I'm sure all of you read this during the test. I'm just going to head straight to answering it. The p-value for Stefan's hypothesis is 0.002. State a conclusion and justify your answer. So what's my conclusion going to be? 5A. No, this is question 6, not 5. Since the p-value of 0.002, does he have any value for us? No. Is lower than any reasonable level of significance, like 0.1, 0.01, or 0.05. So that's any reasonable level. Since it's lower than any reasonable level of significance, we can reject the null hypothesis. We have strong evidence to support the claim that children, and remember, we have to say similar to those in the study. Similar to those, and I'm going to explain why just after this, similar to those in the study who read at different times, afternoon vs morning, will have a difference in test scores regarding the reading. Now the reason my conclusion is for children similar to those in the study is because the children here volunteered themselves. We didn't do a random sample from a given population. The children were volunteered, therefore we can only limit our generalization to the children in this study. Next, explain why it's appropriate to conduct a two-sample t-test instead of a paired t-test. Now, just to review, a paired t-test would be, let's say we take one child, we test him in the morning, we test him in the night, and we record the difference in his scores. And the reason this is important is because if the child read the book in the morning and took the test, what if during the rest of the day the child kept thinking about the test and the questions and what he read, and he started finding the correct answers, and so when he took it in the evening, he gets everything right? So, to answer this question, if a paired t-test were to be used, then a child would read the same book in the morning and afternoon, and then be tested with the exact same questions. It is plausible that a child may get much higher scores in the afternoon due to being exposed to the content already, which is why a two-sample t-test is a better choice for this experiment. There we go, that's the answer for 6b. Now C, the Cohen's coefficient. I'm not going to be going through all this, I'm just going to be doing the calculation right now. So let's calculate Cohen's coefficient. I'm opening my calculator and let's do x1 minus x2. So the absolute value is 17.9 minus 15.2, that gives us 2.7. And now how do we find the standard deviation? We're going to be doing the square root of a fraction, and this fraction is 4.12 squared plus 4.43 squared divided by 2. And that's 4.277809, but let's just divide this in our calculator. 2.7 divided by the standard deviation gives us 0.6311. So let's write that here. D is equal to 0.6311. It's not a negative, it's a positive. Now that we've calculated this, let's look at the next part of the question. Higher values of Cohen's d indicate greater practical importance and lower values indicate less importance. We have these intervals. So based on my answer over here, is his work important? Yes. Well, it's somewhat meaningful in real life. So as per the intervals. Now you obviously want to explain this more, but I'm just going to write as per the intervals. Stefan's work is somewhat meaningful in real life. So in context, you would want to state that his research regarding test scores in the afternoon or morning, regarding when you read it, is somewhat meaningful in real life. That's around what you would say. So now we're on the final section of the test. Suppose the results of his study instead had a standard deviation for the 9 a.m. scores and 3 p.m. scores greater than 4.43. And we're using the same sample and same means. Would his coefficient in this situation be larger, smaller, or the same as part CI? Well, let's do part D, 6D. If we look up here, the formula is dependent on your standard deviations down here, and it's in the denominator. So, and we're being told that we're increasing these values. So, if we increase the value of the denominator, the value of the entire fraction goes down. So I'm just going to write that in here. Increasing standard deviation increases denominator, decreases fraction, lower d value. But then we're brought to this very interesting part. Does this coefficient described indicate that your observed difference in the means would have more practical importance, less practical importance, or the same practical importance? And this is what I would say during the test. So 6DII. If we raise the value of the standard deviations to be 5 each, we get something around, I believe it's 0.5, but this is still within the range of somewhat meaningful. The result of the Cohen's coefficient will indicate that the work is still somewhat meaningful. So unless our standard deviation was increased by a drastic amount, his work is still going to be somewhat meaningful. And that's what I would make sure to note at the bottom. So unless the standard deviation was increased by a huge amount, your work is still going to be somewhat meaningful. Anyways, that's all the questions for the AP Statistics 2025 FRQs. If you have any questions, let me know in the comment section down below. Otherwise, goodbye.